This is Structural Analysis and Modeling Portal section Model and Response Spectrum Analysis of a Complex Structure GSA tutorial part. For this tutorial, you should be able to learn how to conduct model and response spectrum analysis of a complex structure in GSA. You are recommended to go through section Linear Time History Analysis, section Model Analysis, section Response Spectrum, and section Response Spectrum Analysis first. Meanwhile, after we went through the section Response Spectrum Seismosignal tutorial part, you should be able to generate the response spectrum of the pseudo-acceleration from ground motion database via seismosignal. Okay, so first of all, let's create a new file in the model in GSA. So given a job title, that will be, in our case, Structural Analysis and Modeling Portal, with the subtitle of Model and Response Spectrum Analysis of a complex structure and then we can click on next to specify the structure type. So in our case, there will be space. The unit is kilonewton-meter. So beware of the unit of length small because it's used to describe the cross section of the member. And the stress, if you feel confused about the unit of Newton per square millimeter, you can just choose another unit, for example like megapascal. Then we need to generate data from the selected structure type. We use space frame, and for the better illustration, we use the first record in the individual assignment. So there will be 6.5 meter in x and y directions. The number of bay in x direction there's 4, and in y there's 6. The height is 3, so the number of stories is 5 in our case. So for the columns, we can, according to the requirement, that will be the HE 900.8. This one. Finish. And for the beams, that is also in the category Bureau profile IP 600. Next, finish. And for the beam in y direction is the same. So we should include the supports because it will directly generate the fixed condition, fixed restraint of the bottom of the ground floor columns. And we also need to generate story grid plans because we need to define the grid area load later. In this case, we didn't include the self-weight is because the self-weight is included in the dead load that's specified in these cases. However, when you build another model for another structure, and when you conduct another structure analysis, you are recommended to include the self-weight so you don't need to do the math by yourself of the self-weight part. So next and finish. So then you can see our model. So be aware that just then you can only conduct the actions of defining the cross-section of the columns and beams in the beginning if the section properties of columns, beams in x direction and beams in y directions are the same respectively. Otherwise, you should define this value later. So after we define the cross-section, we can click on the section display to do the vision check. Okay. Then we can look at the restraints to see that all the bottom part of the ground floor columns is in cast, which is fixed in all directions. Okay. So then the next step we should do is go to plan view or click on P and select and delete all the interior beams and columns because it's not required in this series. We used select elements and member. Select them all, just delete them. And we also need to select all the nodes and delete them. So if you have previously defined the section property, you see there will be three section properties here. If you don't, like in this case, there's no section property here. So what you should do first is to define the section property by using the wizard here. Give your name as column and specify it. Go to your profile, HE 908. Next, finish, and then we define the beam cross section property. Next, and IP beams for 600. Next, and finish. Then we go to graphic view and change directions. For example, start from X directions. We first select all the columns. And right click, modify selected element to property 1. Then we select all the elements of the beams. We first select in this direction, which is the X direction. Then we change it to the Y directions and do that again. Okay, we can right click to modify select elements, or we can click on the modify selection and modify them to beams. Then we can see that by conducting visual check, it's the same as we built as previously defined. Okay, like in this model. Okay, so after that, what we need to do is to rotate the columns as required to obtain the desired orientations. The reason for that has been specified in the individual assignment hint part. So we need to select all these columns one by one. Right click and modify selection element. Modify orientation angle by 90 degrees. And then the columns change their orientation angle. After that, we need to define the load cases, which is gateway menu, load case specification. And for the first line, use result. So give your name as gravity, that, and live. So we don't need to specify the type. In this case, the gravity loads contains including the dead load and live load. So in our case, that is 1 kilonewton per square meter for the dead load and 2 kilonewton per square meter for the live load. So their sum that will be 3 kilonewton per square meter. But when you are doing conducting a model for designing a building, it's more recommended you define a load case just for the dead load. You should give them the type of dead load, and a new one for the live load. You should give them the type of live load. Sometimes if you have the seismic loading, you also need to define the seismic load. So when you conduct the URS and SLS check, you can combine this load in different ways. So in our case, we don't need them, so just gravity load is fine. Okay. Then after we define the load case, we need to define the grid area load. So we can go to the gateway menu, loading, grid area loads. So select the first line, give your name as first floor, and grid plan that will be the first floor. Okay, and locate there will be locus 1, axis that's global, direction is Z, load value there will be -3. The reason for minus is because the upward direction of the z-axis is defined as the positive direction. So for the downward, which is the gravity's directions, we should put a minus before the figure. So we can define the second one in this order. That will be second floor. So we don't need to change them. It's active 3. We can define them piece by piece. Oh, yeah, we need to change the grid plan to second floor. Yeah, we can define this piece by one by one to the fifth floor, or we can also copy them and using the Excel to generate them. So I select them, go to the fifth floor, and they get like that. Okay, so before that we should check, yep, everything's right. Then we can copy the results here, go back here and paste the result, so that we don't need to define them one by one. This is especially helpful when later you need to build a 10 stories and 15 stories building structure, and if you do that one by one, that's very time consuming. And you can check that at fourth floor, the grid plan is fourth floor, the load value is still -3, the locus is locus 1. Okay, then the next thing we should do is to define the rigid constraints. So to do that, we first need to define, select all the nodes in one floor and save them as a list. For example, there will be first floor. Or here, you can save it at the second floor. Here will be the third floor. Here will be the fourth floor. And here is the fifth floor. Okay, after that we still need to use the abstract view and open the labeled node number. When we define the rigid constraints for each floor, we need to have a master point so that all the nodes is linked to this point. You can choose any nodes in this plan, that's fine, on each floor, but to simplify the process, we choose all the nodes on this column. So at the first floor, the node will be 16.6, and then we go to the constraints, rigid constraints, select the first one, right click, result, and give your name as first floor. Node list is first floor, and master plan node is 16.6. The link type is XY plan, so it just represents the slab on that floor. Click OK. And sometimes you need to define it again. 6. It's OK. Then the same thing for the second one, which is the second floor. Node list is second floor, so we can go to graph view to see that the second at the same position on the second floor, the node number is 101. So that for second floor, node is second one, that is 101. It's XY plane. Yeah, as always, we need to define it again. 01. It's okay. Right, then what we can do here is we can do like what we do in defining the grid area laws one by one, or we can copy them in Excel and generate it more easy way. So we first of all select them and generate a 5 rows. So there is a problem that as you can notice at column E. See here, it's not first floor, second floor, third floor, fourth floor, fifth floor. And it's especially important since this part showing the which grid, which node list you are talking about. So what we can pay a small trick by delete all this, and then we make it to fifth floor. But later we need to do that hand by hand, or you can use the function of, for example, in here, press Ctrl H and replace them as floor and floor, like that. Place all, and but so to do that, all, and for the first, can do that, all, second, third, fourth, and fifth. Okay, so then we select from the left hand side, copy it, go back and paste the value. So we can check at, for example, at fourth floor, the node list is fourth floor, the master point is 171. The reason I can do that is because there is a pattern for the nodes in these columns. The difference between here, 66 and 101 is 35. So as here, and here, and here. So I can use Excel to generate that. Otherwise, I need to record all the numbers here and then go to rigid constraints and input them one by one. Then to visual check whether we have set the rigid constraint right, we can use the labels and display methods on the right hand toolbar and select the rigid constraint, press OK. Then we rotate a bit and you can see that is all rigid constraint to here and it's only XY plane. Okay, so we can close it. It's not required to constrain the nodes in only one position. On each floor, you can constrain it to any points on that floors. Doing that is just for easy illustration, as mentioned above. Okay, then after we create the rigid constraints at every floor, what we need to do next is to create a new analyze task for the gravity analyze. So we go to Gateway menu, cases and task, analyze task. At the empty area, right click, new analyze task, or we can use this one, this new analyze task from the top toolbar. So first we name it as gravity analyze, and the analyze type that will be static. Okay, and we can click on next. We need to add lowercase 1 in it, double click, so L1, and then we press next and finish, and we can start the analyze itself. Then we can go to the Gateway menu, Output tab, the global results, total loads and reactions, and check the value here if it's the same one as what you have been calculated by hand calculation. If it is, then we can carry on to conduct the eigenvalue analyze, which is also go back to the table tabs, analyze task, add a new one, give it a name as eigenvalue analyze. So the analyze type in here, that will be the dynamic model analyze. So for the numbers of the mode, actually it will influence the ratio of the effective mass to the total mass. So the higher the number is, the value is more higher. And according to the code, it's required that the ratio of effective mass to the total mass should be larger than 90%, which we will check later. So here we can input 5, like we have 5 story, or we can input 15 here to make sure that the effective mass to total mass is 90% the ratio. Then we need to make sure the mass option here, the lumpness at naught here. And then for the code, for the case definition, we select load 1. Direction is Z because it's vertical. And then we don't need to change others, but just click next. So before that, it's also worth mentioning that actually if we input 5 in here, the ratio is still larger than 90. So you can check later. So then first thing to do is to go to the output tab and to the global results, go to the dynamic summary, and see here provides the ratio of the effective mass to total mass. So here you see the value is definitely larger than 90%. Okay, so then we can go to the graphic area and we can go to the plan view, select case as Eigenvalue model 1 and click on the deform image so that the mode 1 the structure is deformed in the x direction, and in mode 2 is deformed, is vibrate and the y directions. We can also use the animate, which is at the right hand toolbar, to see how it vibrates. The first one. For the third one is rotate. So for the third mode, so it's rotate like that. Okay. So the first 3 modes usually is quite important to check. Then after we have verified the eigenvalue analysis, can go to the we can conduct the response spectrum analysis. So let's go back to the gateway menu, table tabs, dynamic response, response spectrum. Click on the first line, use result, and click on user define. Set the damping option as constant for 5%, and then get the results from the seismic signal. We can copy it and paste it here. Then we can have a look at the spectrum 1 diagram, which is the acceleration versus period. Beware that the acceleration here is a pseudo acceleration, and you should be able to understand the difference between pseudo velocity, pseudo acceleration, and velocity and acceleration. Finish. Then we go to the case and task, analyze task. We build a new analyze task, which is the response spectrum analyze. And select the dynamic response, response spectrum analyze. Go to next. So the model analyze task should choose task 2. Okay, we just calculate. The combination is the CQC, which is the most accurate one. Axis is global. Directions is just X and Y because we want to see its reactions in X direction and Y directions. Then just ensure that you select rigorous. We don't need to use fast because it's quite a small model. And then we can finish and start to analyze. Then we can go to the output tab and go to the total loads and reactions under the global result. And at cases, we select case 17 because it's the response in X directions by the combination of CQC. So you can check the result here and compares it to what you have calculated by hand calculations. Also in case A18, that's for the Y directions. So you can check the results and compares to the output of the hand calculations. Okay, so that will be all for the GSA tutorial for the model and response spectrum analysis for a complex structure section.